you want?
I don't care.
Would it be 0?
It would be 0. Why 0?
Because they're in the same line together and they gotta cancel out.
Well, I think there's some circular logic there. What is the direction of acceleration? Yeah,
Left.
that way.
Left.
Therefore, up and down is 0.
Right.
All right. Jacob, will you give it a shot?
So y sine theta plus f cosine theta equals ma.
There we go.
So why was the w, why is it minus w?
Because it's going in the negative direction.
Okay.
It's plus in front of all the things in the positive direction, minus all the things in what are the negative direction.
But like you said, if you add those two together first, then you don't have the two forces, and it would be y cosine theta subtract the addition of f sine theta and weight.
Right, yeah.
Put
So-
the parentheses like you said, but
Yeah.
I just wanted to. That is the same thing, correct,
Gotcha.
Yeah.
correct.
Then, does this make more sense to you, or that?
Yeah, I don't know if it's like just a visual thing, like the f sine theta and w, since they're in the same direction, I'll almost want to have it plus, I don't know.
Okay.
But I understand, like the top one looks better and I can see that it goes to negative.
Okay, I need to take note of that and in the future, emphasize that more. Kano,
So why does the first equation equal 0? Why does the second one equal ma?
which way is it accelerating?
It's accelerating to the left.
Yes. This first equation is horizontal, it's vertical stuff. It's up and down. So that's why, because it's mass times acceleration in that direction. And since acceleration is that way, there is no acceleration this way.
Okay.
That's why it's 0.
Okay, thank you.
Substitution. This time we have 3 things. Yeah. All right, weight, as in the force. Formula for weight, oh, in unison, please.
mg.
That was better. Not the chorus of angels that we'll get later when we get to energy, but. All right, so we have mg there. Acceleration.
V squared over r.
There we go. And what is the other one for which we have an independent formula? Amy, did you say it?
Would it be the omega squared r?
Say it again.
The omega squared.
Oh, looking for the other, we could use omega squared r, still v squared over r I think is gonna work better here. The other variable for which we have an independent formula. It's not normal force. And there it is, friction. So we have a formula for friction here. All right, so let's rewrite these in an ever-fading marker. So I have y cosine theta minus my formula for friction. Mu times y, technically mu sy, times sine theta, minus, I'm going to go ahead and move mg over also. mg, and then we have y sine theta plus u sy cosine theta equals m v squared over r. Questions to hear? We're about to do some fun math. That's right. All right, the more I write down, the more chances there are that I'm gonna make a mistake. So I'm gonna do a couple bits of substitution here. Technically, it is static friction. So I'm just gonna write mu for mu sub s. I'm gonna write s for sine of theta and c for cosine of theta. I'll substitute back in at the end, but I'm just going to do these shorthand just so I don't have to write as much. And so we now have yc minus mu ys equals mg, and ys minus mu yc equals mv squared over r. There are other substitutions you want to make just to make life easier. Some people have difficulty drawing the mu, just don't use m for it. So the classic mistakes. Probably the biggest classic mistake is confusing the coefficient of friction, this mu, with friction itself. Mu is just a number. To my knowledge, it's never bigger than 1. I suspect that there is something out there, I just haven't seen it on any table where mu is bigger than 1. It has no units. Friction is a force, it has units. I need to get rid of my normal force. Because in this problem, well, mass is going to end up canceling out, so we don't have to worry about that. G, we know, because we know where it's taking place. V, we know, because that's the problem, 50 meters per second. R, we know, because that's given. Theta is what we're trying to find. Oh, we know mu also. Normal force we don't know, let's get rid of it. So I'm going to factor it out of both equations. So I have y times cosine minus mu sine equals mg. And then y sine minus mu cosine is equal to mv squared over r. Got Ian?
Wouldn't the second one be plus?
It should be plus. Thank you for catching this now, as opposed to like going later on and going, wait a second, where did I miss my minus sign? Now to get rid of y's, I could solve for y and then plug in, or save a step and just divide, just like I did before. My y's cancel out. I don't get tan theta though. That's what makes us more of a nuisance. And then we end up with gr over v squared. Now some students like to plug in numbers early on as opposed to waiting until the end to plug in numbers. That's fine. If you try to plug in numbers too soon, you'll end up with this issue of, wait a second, I don't have a mass. Well, just make up a mass. It's not given to you either because I made a mistake or you don't need it. In this case, you don't need it. So make up a number that's not 0. But we do have a single unknown, theta. Theta is our unknown. We need to solve for theta. So first off, I'm going to get rid of fractions. I'm going to cross multiply, or I could treat gr over v squared as a number, but I need to get rid of, I have thetas on top, thetas on bottom, I need to get rid of it somehow. So I'm going to erase some stuff. We'll reproduce some of the stuff later. Matter of fact, I am going to do the gr over v squared is just some number, and I'm just going to let that be a. Why not? Capital A. So I have c minus mu s equals a times s plus mu c. So I just multiply both. Since I made my right-hand side just as letter A, you can use a calculator with our numbers and figure out what it actually equals. Bless you. Just multiply both sides by this denominator, so, or cross multiply it if you'd like. So I have C minus mu S equals A times this. I distribute. Where I'm heading here is I want to get all the sines together and all the cosines together. So I get C minus mu S is equal to AS plus A mu C. And so get the sines together, and the cosines together. So I have C minus A mu C is equal to AS plus mu S. And now I'm going to factor. I'm going to factor my cosine out over here. And I'm left with 1 minus A times mu. I'm going to factor my sine out of the other side. A plus mu. Fortunately, we are not going to have to square anything and end up with a quadratic. I'm going to divide both sides by cosine times A plus mu. So on the left-hand side, my cosines cancel out. On the right-hand side, my A plus mu cancels out. So I'm left with sine of theta, let's go ahead and put that back in, over the cosine of theta is equal to 1 minus A times mu over A plus mu. And hoping I haven't made a careless error. We'll soon find out. That's equal to the tangent of theta. Let's go ahead and stick in our GR over V squared over there, just to parallel it to, or connect it with what we had just done. 1 minus UGR over V squared divided by GR over V squared plus mu. Now, if I were doing this on my own, I would have actually solved for a value for A by now and just use that number. But what I wanted to do is, what happens if mu equals 0? In other words, back to the frictionless situation. If mu equals 0, this would become 1 over GR over V squared, which is just V squared over GR is equal to the tangent of theta, which is what we did. We had that equation before. This tells us that we've done something right. Of course, if my signs are off, then that would not show up here. But we've done something right. Now we plug and chug. One minus 0.9 times 9.8 times 100 over 50 squared divided by 9.8 times 100 over 50 squared plus 0.9. So that's roughly 6. So this is roughly 0.64 divided by 1.3, roughly, which is about 0.5. We're about to get the real number, just a minute. Okay, Madison?
On top,
All right, someone else?
Point 6472 is the top number, no, yeah.
6472?
Yeah.
All right.
The bottom was actually 1.292.
292. And the ratio? Oh,
1.292 on the bottom.
292. Thank you. Thought something was off there.
Point 3.
No. Oh, 0.292. 1.292.
Okay.
Not the 1.92 as I originally wrote it.
I got 0.501.
And that's equal to the tangent of theta. And therefore theta is
Degrees.
26.6.
Hmm?
1.61 degrees.
Okay. So ideally, without friction, this thing needs to be at a, I think it was a 68-degree angle, but we can start lowering it until it gets to about until it gets to 26.61 degrees. At that point, this car will definitely slip going 110 miles per hour around this curve. If roads are wet, that number will drop even more. Or, sorry, that number will drop, it means that number actually will go up. We're not going to go through the problem, but I at least want to set up the maximum angle. Any questions before I at least set up the other problem? So we had car here, normal force going this way, weight going down. Now I want to know what is the maximum angle so it doesn't start sliding down the ramp. So which way will friction act at this time?
Could you ask the question again?
All right. So we had that ideal 68-degree angle here. And then as I start increasing the angle, at what point will it start to slip? Or what is the maximum angle where it doesn't slip and slide down?
So you're asking what direction accelerate, friction is
Yes.
up the slope.
Yep. Because the car vehicle wants to slide down as I increase the angle. So friction is acting this way. So when we break it up, we have weight acting down. we have y sine theta acting to the left, we have y cosine theta acting up, none of that changes. What changes from what we just did is the direction of friction, which is now to the right and up. So this will be f cosine theta and f sine theta. Again, because they're perpendicular, the trig function involved changes. It flips from what we had before, or for normal force. My acceleration is still to the left. Set up the same coordinate system. Well, let's at least get the equations of motion, I hat and j hat. Brandon, I was going to pick on you again, unless you don't want to do that this time. You want to pick on someone else?
No, I'm bad.
You're okay? As in, you want me to do someone else, or
I'll pass this time.
you'll pass this time? Okay. Jacob, do you feeling like you want to do it, or you want me to pick on someone else?
I can try.
All right.
Okay, so are you, for the equations, are you saying?
Yes.
Or- So it'll be y cosine theta plus f sine theta plus or minus w.
It is one of those.
Yes. It's minus because it's the opposite direction, right? And it's gonna equal 0.
There you go. All right, now the other one. Jay, how confident are you feeling right now? You want to give it a shot? All right, that sounds like the enthusiastic response I'm wanting. Y sine theta. Yep. That's it. Equations of motion. Now, in this particular case, if you worked it all out, went through the same process we did before, you'll end up with an angle that is, I think you end up with a negative angle. Because what, in this particular case, that thing can be perfectly vertical, and at 50 meters per second, you'll be able to go around without slipping. If you can't picture that, if you've ever done the Oaken bucket, well, actually Craig probably the only one in here who could have been on the Oaken bucket. Similar amusement park rides where you get into it and it starts spinning around and you don't slide after the floor drops. It's that type thing. If you're spinning fast enough or traveling fast enough around the curve, the normal force is so great that the friction up, the maximum static friction up exceeds the weight, and so you do not slide.
And yes, I remember.
All right.
Carowinds, yes.
Oh, yeah.
I hated when it went away, but anyway.
Just because it was probably unsafe or
Oh,
lead
sure,
paint or
I have
whatever.
no doubt it was unsafe.
Lead paint and asbestos. All right. Any questions before we bring in a different type of circular motion? All right. Up until now, the gravitational forces we have dealt with have always been the weight. But now we're going to go beyond that, make it more general. talked about the fact that a requirement for gravitational force has to be that there are two masses. And so now let's deal with that. The generalized gravitational force, F sub G. It is a vector quantity because it's a force, but we're going to start out with the vector piece of it, and then we'll bring the vector into it. So it depends upon two masses. So if I take two masses here, there's a gravitational pull between them, I'm claiming. And so there's some force between them. So if I switch the masses, and assume that they're the same distance apart, I switch the two masses, what changes with the gravitational force? Sorry. It switches with it. What about the strength? If they're same two markers, assume same distance apart, the strength of the force versus the strength of did I say magnetic? Gravitational force versus strength of gravitational force. So no changes. What you're going with?
The direction.
Okay, which goes along with what Ahmad J. was saying, is that it flips. All right, so by flipping the masses, the strength doesn't change. There are only two mathematical operations that we deal with on a regular basis where I can just flip things and I get the exact same answer. Multiplication and addition. So whatever the force is, it either depends upon the addition of the masses or the product of the masses. And I'm just going to spoil it. It's the product. I'm leaving a space up here, which I'll explain in a moment. Now, I mentioned the same distance, because distance does have something to do with it. If two objects get farther apart, does the gravitational pull get stronger or weaker, based on your gut feeling?
Weaker.
So as r goes up, the distance between them goes up, I should be getting a smaller number here. Now for no explanation, it's squared. Just because that seems to be the way nature is. There are some groups who actually study to find out, is it really squared? Maybe it's 2.0000001 or 1.9999999. And so what they basically, it really does seem to come out to be close to squared. They haven't nailed it down. All they can do is say the difference between 2 and what we're finding is less than, and then they give some upper limit. And now this mysterious thing up front. The units of mass, what is the SI unit of mass? Everybody.
Kilogram?
There we go. Again, unidirectional single voice, but man, the way that you projected was awesome. SI unit of distance.
Kilometer?
SI would be meters. All right. So I have kilograms squared over meters squared. And what's the SI unit of force?
Newton.
So somehow we need to reconcile that. And so what this number here is, a good bit of what it is a unit conversion bit. This is known as the gravitational constant. I am going to parenthetically stick up front, universal. The reason I put it in there at all is the fact that some textbooks, especially older textbooks, will call it universal gravitational constant. The reason why it's parenthetical is we really don't know if it's universal or not. It's rather presumptuous. We're sitting here on a planet in the middle of a galaxy, in the middle of the universe, or somewhere in the universe, and we have the gall to say something is universal. Because the universe is not behaving the way we'd expect it to. The things are moving away from each other. You know, if you think Big Bang, things explode, move away from each other, but they're moving away faster than we expect. And so one possibility is that this is not universal. Another possibility is that there's something out there that we can't see causing it, and that is the birth of this idea of dark matter or dark energy. They are not the same thing. It has a value, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. It is also one of those things that sometimes students will just call gravity. The four things that students sometimes will call gravity are weight, generalized force due to gravity, acceleration due to gravity, and the gravitational constant. Which is why I sometimes will nitpick, or often will nitpick, if you say, where do we get 9.8 from? And someone says gravity. You know, things are more specific than that. Gravity is a very huge topic, and there are these little bits that we are glimpsing. This is the gravitational constant. It is not gravity. Masses, hopefully you're somewhat comfortable with what masses are here. R is the distance between the masses. So the question I pose to you, is this surface to surface or center to center? What's your gut tell you?
Center.
Center to center.
All right, and it is indeed, your gut's right, it is center to center. We know it can't be surface to surface because if I went outside and put my hand on the dirt, I'm not stuck there. If it were surface to surface, then if foot touched the ground, R would be so close to zero, the force would skyrocket because my denominator gets tiny, and we know that we can, it's been known to happen. I can jump when I'm standing on the dirt, even in bare feet. True story. So let's say I have a mass one of 500 kilograms. A little over half a ton. And then I have let's make this 2,000 kilograms, and they are